Good afternoon, everyone. Today, my team and I will walk you through some modeling options for forecasting the Higgs boson signal. Our team of data specialists has prepared a presentation walking you through some simple and complex models, giving you the option between descriptive and accuracy. So we'll start with some EDA, followed by I will introduce the simple decision tree and a random forest, a more complex model with better accuracy. Denis, our reducing dimensions and boosting specialist, will focus on walking you through these options and why and how they can improve your model. Ismael, our support vector machine specialist, will walk you through this model and explain what are the benefits and how they can improve your model. Closing with our next steps and what we would do if we had more time. Let's begin with some EDA.
Hi, so beginning with some EDA, this is just you've seen this before, just a correlation plot of the different variables of the data set. So just to give a brief snapshot of the relationships between the variables, but then we also wanted to just provide some zooming in scatter plots. So this is some scatter plots between selected primitive variables. Next, also some scatter plots between the derived variables. So this is between delta, eta, jet, and okay, so the primitive variables were the variables that were measured, and then the derived variables were based off of, or computations based off of the primitive variables. They were given in the data set. Next, we also just want to look at some scatter plots between a derived variable and some primitive variables. So moving on with the first model, the classification tree.
Thank you, Ismael. As you can see, there wasn't much that we can see with those scatter plots. There was a lot. So we decided to fit a classification tree model, just a basic model with all the parameters to see if what we would get. And the good thing about a classification tree is that it's really easy to interpret, and it's very descriptive. Although on the flip side, they tend to have a lower prediction accuracy. For our first basic tree, without any pruning, produced an accuracy of 72% with about 4,000 terminal nodes and an AMS score of 1.132. On the right-hand chart, you see a chart with the misclassified observations and the terminal nodes. Tells us that about 5 would be the correct pruning of the tree. So I tried a 5, and it turned out to give me a lower AMS score than all the variables. So then I increased it a little bit to 10, and it gave me a slightly higher AMS score of 1.24. So taking a look at the tree, we see that the derived lip eta centrality column is at the very top, meaning it's the most influential to the signal, to predicting an accurate signal. And the way it's read this chart, if it goes to you look at this variable, and if it's lower than 0.005, you move down to the left, and if it's greater, you move down to the right, and so on. And that's why it's a very easy model to describe what it's doing. It's not the best option for predictability, but descriptive is good. So I tried a random forest. We tried a random forest. It's a more robust model with greater prediction, predictability. It's the average of a collection of trees, and it results in like an ensemble with the average of the collection of trees, although you lose descriptive abilities. So we ran this random forest with all the variables, and on the right-hand side are all the variables. So I decided to maybe try cutting it past the 14th variable, because then it becomes not so influential. This first model gave us a score of 1.781, which is impressive because just changing the models with all the variables, and the score increased by over 0.5. So this is the second model we tried for the random forest. And we tried with the 14 variables, and we added 2 new columns where they looked at the NAs in the mass transverse met leap column and the delta eta jet column. And for some reason, it increased the accuracy to 83.5% with an AMS score of 2.795. So we selected 4 features at a time at random with 500 trees for this model. So it gave us a really good accuracy. My colleague Denis will walk you through the reducing dimensions and boosting.
Okay, so usually when we say reducing dimensions, the thing that comes into people's mind are that you're reducing the amount of data. So the question is, why do we want to reduce data? It doesn't always mean that it'll have a negative outcome. Sometimes it'll actually improve the data by decreasing the multi-collinearity. It also decreases the storage. So if you're running out of space, that works out. And if your computer's not fast enough, then it'll also reduce the amount of time or computational power required to run your model or to run your algorithm through the data. And another perk of reducing the amount of variables is being able to visualize the data. So with this, we had over 30 variables, and being able to visualize it in, 30 dimensions, if you want to think about it that way, is pretty difficult, whereas we're used to seeing 2D and 3D. So if you're able to reduce things down to that many dimensions, it'll make visualization a lot easier. So here's a scree plot doing PCA, and we can see that up there, that first PCA includes approximately 12 of the variables, and it eventually drops down lower and lower as you include more, eventually nearing the 1 line. And that 1 line tells us that at that point, a principal component will represent approximately 1 variable. So if it's above that, it's going to represent more than 1 variable, and that's what we're looking for. So after running this, here's a table showing that with the principal components, we're basically taking different ratios of the different variables and putting them together to create new variables. In this way, we're able to capture more of the data in less variables. So as we can see, 40.9% of the variables is represented by principal component 1. And after doing all 8, we're able to capture 81.6% of the variables. Okay. All right, thanks. All right, so why did I not decide to do this? Well, even though this is great and it helps with reducing the amount of dimensions, it was a little bit difficult to interpret because we're combining a whole bunch of variables to make these new variables. So then we looked at Lasso, and running this, Lasso reduces the dimensions of most of the variables down to 0 by scaling them down and shrinking them. And after that, we have approximately 12 variables remaining. An interesting find is PRI JetNum, which in the original data set was a categorical value with values from 0 to 3. And that was split up into dummy variables with columns of JetNum 0, 1, 2, and 3, respectively. And Lasso found that only JetNum 3 played an important role. So yeah, that's all great doing dimension reduction, but does it actually make a difference? So I ran GBM with all the variables with certain parameters, trying to pick the best, and I got an AUC of 0.78, and that gave us an AMS score of 2.11. Now, after applying it with the variables, with the 12 chosen variables from lasso regression, we have an improved AUC of 0.85 and an AMS score that jumped up by 0.16. Now, that wasn't that high of a number, and so we decided to skip the PCA portion, calculating the new PCs, and just move on to another machine learning method and see whether that will increase our score. So now Ismael will talk to us about SVM.
Okay, so finally going on into the last model that we ran, something more predictive based. We attempted to use support vector machines, and in this case, we identified that this was a nonlinear problem, judging by the scatter plots earlier, that there was a lot of overlap. So we chose a radial kernel for SVM. And then just some pros and cons about SVM. So it's a good choice in terms of for effective in high dimensional spaces, and then also the choice of kernel gives you the flexibility depending on the problem. Just some cons. As with anything solely focused on prediction, there's a trade-off in interpretability. And also, SVM in particular has a problem in terms of computation time when the data set is very large. So when we ran our SVM on the data set, we tried to incorporate the results from the random forest model, wherein we chose the top 14 models, top 14 variables in terms of significance. And then we also tuned the threshold to 0.7. And we got an accuracy of about 0.81 and a resulting AMS of 2.72. Now, finally, our model recommendation. So as you can see, we ran several models, and we wanted to show you what our final model recommendation would be in terms of the Higgs boson problem. So overall, we chose the model to recommend random forest. One is that this had the highest accuracy in terms of AMS score, so it was about 2.8. Close to second to the random forest was SVM, which was about 2.7. However, we chose random forest for a couple of reasons. One is that random forest is easier to tune and train in terms of like parameters, and also because of the disadvantage of SVM and its computation time in terms of a large data set, that was a factor in the choice. And then just a little addition, in terms of pure description and in context, if like the audience was not so technically adept, we would recommend the classification tree. Now for our next steps, we would want to incorporate in all of our models some feature engineering. And also considering that we ran several models, we'd want to combine them in some ensembling methods. Thank you.
Questions? Yes.
Just, I'm curious, why did you tune threshold to 0.003 and 0.7
What model is this?
Why didn't you use the same threshold? Yeah.
So with SVM, I was tuning it. I originally had, I was coming up with like 0.3, and then when I was trying different thresholds, my AMS was better when as I approached 0.7.
So is the threshold on probability? Like
Um,
like how did you implement the 0.7?
so that was just trial and error.
Was that from the output from the chart that you got?
No, it was just something I tuned myself.
Did you do the SVM on the entirety of the training set?
No, I did not. So my methodology with SVM, because it took so long to compute on the entire data set, I chose to run it on 1% of the data set. I know that's extremely small, but my goal for the project was just to run the algorithm on the data. So I chose 1%.
Whatever on this page is from that 1% of
Yes. Yes.
The other question I have is the cost parameter at 7.5. Was that something, because on the formula it says best radial model, that's something you cross-validated, or that's something you kind of gave without?
Oh, so that was the cost and the gamma are both from cross-validation on the 1%. So everything, the whole algorithm was run on 1%.
So first thing I want to do is actually commend this team a little bit, because every team has had a really good presentation so far, but this is the first time I'm really getting the descriptive element of anyone who went yesterday. So thumbs up to that. I like that you're giving me the balance of description and accuracy. Can we go back to the decision tree? 3 questions I want to ask. Kelly, so you were presenting this to us. So I'm noticing on this tree, especially for the right-hand side, we've got a branch that's got B, and then we have another branch that splits and it's got S, and then it goes back to B to S, and then finally a branch with B and S. And we can kind of see that relationship for the entirety of the tree. There's basically what I'm saying, there's no node that's split and give you the same classification. So we never really talked about this before, but can you think of a reason why this might be manifesting for this data set? Why every time we sort of add a branch, it's flipping back and forth between the groups?
Well, every terminal node, it asks a question, and it has a threshold, and it says, if it is whatever the threshold is, then it goes. If it's less, then it goes to the left, and if it's greater, then it goes to the right. But I'm not sure of your question on. I mean, if everything is met down to here, then it would be B, and then so on S. But I'm not sure of your question.
So what I'm basically getting at is that for this data set, it's kind of hard to segment the data into regions that are bosons or signal, whatever the S and D, I forget what they represent, the S region and the D region. Right? Every time we made a cut, we're trying to slice out another little chunk that might be one group.
Yeah.
Might be another.
Yeah.
There's no splits here where we make the nodes more pure, right? We're kind of just
Yeah. Yeah.
It's kind of like we keep trying to get better and better by siphoning down.
Yeah. Yeah, and I mean, the very basic tree that I did had almost 4,000 terminal nodes. So ideally, you wouldn't want to use this model, but if you wanted a model where you can describe it, then yeah, you can use this model.
Question, can we go back to Denis and PCA? I think you may have said something, I was taking a note. You mentioned that the first principal component contained about 41% of the information. Did you come up with a descriptor for what that first principal component represents?
No, I didn't. But yeah, I didn't bother calculating it. But if we have a look, we could see which number is the highest in the principal component 1 column and see which variable contributes the most to that.
So I'm a little bit unfamiliar here, but we've got some really positive numbers and we've got a couple that are negative. So I know part of the discussion we had was principal components still incorporate all the variables. Let's cut some off and proceed forward. Maybe that's one way the first principal component represents the differentiation between these positive and negative values. Maybe choose one representative of each group and move forward with those. Potentially, not necessarily. Important to interpret what the principal components means because that gives you the value. Unsupervised. I forgot who was talking for the GBM model V2 slide. The last question, I'll throw this to the entire team. What is sensitivity and what is specificity?
Right, it has to do with the false positive and false.
True positive and
That
false positive.
So what is the sensitivity?
The sensitivity is the true positive, and of the accuracy. Are you forecasting something accurately? That is so like.
So it's correctly identifying in the problem signal.
So phrased as a conditional probability. What is the sensitivity?
So if it was a background noise, then and we forecast it correctly, then that would increase our sensitivity as well as if it was a signal and we forecast it correctly. Now if we forecast it incorrectly,